Teragamma servomotor control compensates for resonance, reducing vibration and improving motion accuracy and speed.
Hi, I'm Chris Cullen of Teragamma Motor Control. In this video, I'll show you how easy it is to improve performance on a servo-controlled axis that has a resonance. Resonance can not only cause vibration, but it can add instability to a closed-loop controller, limiting the achievable bandwidth.
This demonstration axis has a stiff bellows coupling and does not have a significant resonance. Self-commissioning synthesized stiff position controllers. A tracking controller with a bandwidth of 149 Hz and a regulator with a bandwidth of 154 Hz. It has excellent step and settle performance, as we can see in this plot of 10 one-revolution steps laid on top of each other. You can see that the motor position enters the 5 encoder count in position band in 1.2 milliseconds, and it settles to 1 encoder count in about 7 milliseconds. Now let's introduce a resonance. We'll remove the bellows coupling. We'll replace it with a spiral coupling made of aluminum, which is much more flexible and introduces a resonance. We'll commission the axis with the same parameters as before. However, we'll disable automatic resonance compensation. Now run self-commissioning. Self-commissioning identifies multiple models, including resonance, of the motor and axis, and designs closed-loop controllers. For this demonstration axis, the process took about 5 minutes and was completely autonomous. Let's see the controllers that got designed. The default controller, a tracking controller, has a bandwidth of 39 Hz, and the regulator a bandwidth of 43 Hz. That's a lot less than for the bellows coupling. Let's try running the same motion script as before. 10 steps, each 1 motor revolution. In this case, the settling time is much larger, 39 milliseconds. Let's look in at the settling phase. In this case, we can see that the performance is sluggish because of the limited bandwidth of the controllers. What happens if we increase the bandwidth? We'll bring the regulator bandwidth from 43 up to 110 Hz. That's much less than in the previous 153 Hz bandwidth. Notice the protection is automatically enabled. And we'll just move 1 step. Notice that the control immediately became unstable and faulted. Now let's try to fix the resonance problem. We'll open the vibration window. Notice that self-commissioning has already identified an open loop resonance at 533 Hz. We'll put a notch filter at that frequency in the torque loop. The torque filter is inside the position loop, and so care must be taken to get the settings right to avoid instability. We'll use default settings for notch width and depth. You can also set the frequency and damping ratio of the numerator and denominator transfer function directly. We'll set up to use this notch, and we'll configure it. Notice that it immediately becomes enabled. Now we'll check to make sure instability protection is enabled, and it is. Okay, let's try moving. 1 revolution. And there's no more instability. You can now manually search for the highest feasible bandwidth. This is the way you have to tune a controller using even the easiest to use competing products. Teragamma provides an easier way. It will relearn both controllers, regulator and tracking controller, using your new configured filters. All you do is execute this menu item, and here we go. That's all there is to it. Now look at this. We have a regulator of 144 Hz, a tracking controller of 140 Hz. Note that not only bandwidth, but all parameters such as damping, patience, and various filters within the control loop are optimized. Now let's run the test motion script again. Remember, it's 10 steps, each 1 motor revolution. Look, this is the same planned step time as for the bellows coupling, and the max settling time is now 9.1 milliseconds. That's much better than before. Teragamma tools will help you refine a resonance configuration as well. The vibration window will attempt to find a resonance in the most recent recorded motion. Let's see what it can do with the 10 steps. Well, it found something. In the position error signal, it found 13.5 cycles at 243 Hz. Let's let this option continue. It configured a command filter, robust type, at that frequency, and it chose an appropriate damping ratio. It's already enabled. The command filter filters the position command and feed forward so that this frequency doesn't get to excite the system in the first place. All right, now let's try the motion with this filter configuration. Now look at that. The planned motion time has gone from 22 to 26.5 milliseconds. That's because the command filter takes a little extra time. However, the settling time has gone way down. In fact, the maximum total step time is almost as good as with the bellows coupling that didn't have a resonance. And the settling, as we can see, is excellent.
You've just seen a brief overview of Teragamma vibration compensation. It allows almost any servo axis to achieve remarkable performance. Thanks for watching.